Okay. Hello, everybody. Let me know if you can hear me. I see Nana is here, Lamine is here, Victor is here. Welcome, everybody. So glad to see you all here today. We're trying a slightly different setup today, so get ready. How was everybody's weekend? Victor said they had a great weekend. Tulalupe says hello. How am I? I'm doing well. Good to see everybody here. So, what would you guys like to focus on? What should we be working on today? Tulalupe says, sorry for the wrong spelling, Nicholas. Don't worry, there are like a million different ways to spell Nicholas, so all of them are valid. The important thing is you remembered my name. So I see we have 7 people here in office hours. What would you guys like to focus on? Is there a mini project or part of the curriculum that you'd like to look at? So Nana says they have a general question, and here's the scenario that they propose. So let's say you've built a model, your predictor, and you predict some outcome that will happen in 3 months. So you decide that you predict that there will be an earthquake in Los Angeles in 3 months. And then 3 months passed, and there is no earthquake in Los Angeles. So is your model bad or good? And how do you measure model performance? Well, it's very hard to measure model performance if you only have one data point by which you're measuring. So if you're predicting just one event happening 3 months from now, you're going to have a hard time. There are several ways to, um, so there are several metrics that you can use to evaluate whether your model is performing well or not well. So let's take a look at a few of them. Let me change my screen so that we're all looking at the same web browser. I have a slightly different layout today, so you should be able to see my face on one part of the screen. Down below me, you can see the chat if you're tuning into office hours after we're done. And then on this side, you should see the website. So I'm going to click on Data Course. Oh, my server's not running. Let me start my server up again. Okay. This is in fact the wrong server. I'm sorry, guys. I got my office hours confused. This is for Unit 1, but you guys are Unit 2. You're the veterans here. What do you guys think of the new layout? So, what are some... Oh, great. I'm glad you guys like it. So, what are some ways... So what are some metrics that we use to measure the performance of a model? What are some... This could be categorization or it could be regression. What are some that you remember that we've discussed up until now? So I'm going to open the ML Metrics notebook. Can you guys let me know if this text is big enough for you to see, or would you like it bigger? So Tulalupe's already got a few. Accuracy is one. Precision, recall, these are all good ones. So let me answer Nana's question kind of globally, and then let's look at some particulars. So Nana says that they've formulated their question, and they say, let's say you're predicting defaults, oh, like mortgage defaults, and for a cohort you predicted some defaults, and say in 3 months only 40% of your predictions were correct this time around. So the first thing that you need to keep in mind when you're evaluating a model is what is your baseline level of performance. So if you're predicting mortgage defaults, what is the current model performing at, right? Maybe the current model your company is using is only right 20% of the time. In that case, predictions are going to be fantastic if you're hitting 40%. However, if you know that your model, let's see here. If you know, for example, that generally 40% of each cohort default on a loan, then you could just have a sort of a naive predictor, which would basically 40% of the time say, okay, this person's going to default. So that's not particularly good. Well, let's look at the categorical ones, actually. Let's look at categorical ones specifically, since this is the let me import metrics. Hold on. Okay, great. Okay. Okay. So I want everyone to look at this figure for precision and recall. And let's just quickly draw let's connect this figure to our discussion of housing mortgage defaults. So here, let's say the 0 parallel here on the y-axis is the same as, excuse me, those are people who did not default on their mortgages. And then the people at 1, those are the people that did default. And then the colors correspond to our predictions. So the blue are the people that we predicted would default and did default. And the people who are purple are the people who we said would not default, but in fact, they did. Okay, so let's just talk a little bit about accuracy. So I want to talk about first accuracy, and then I want to talk about recall and precision. So accuracy would be how many of my predictions are right in this categorical or classification problem. And it's often the default score or metric that we use when evaluating the fitness of a model. For example, Nana said, hey, 40% of my predictions were correct. That's how she's evaluating the model. Now, the question then is accuracy always a good metric? And the answer is no. Let's give you an example. Let's say I have, let me pull up my iPad here. Good. So let's say I have two, all right. Let's say I have a feature space and I have two groups, and 90% of the observations in this group belong to the blue class, and 10% belong to the red class. Now, if I had a predictor that always predicted blue, it would be accurate 90% of the time, because 90% of my observations belong to the blue group, while only 10% belong to the red group. And that's why when we're talking about, that's why accuracy, especially when you're dealing with some sort of classification problem where they're unbalanced classes, for example, mortgages, right? I would imagine there are a lot more people that pay their mortgages than people who default on their mortgages. Accuracy is not always the best measure. And so there are a few options that we can use. The first is recall. And recall is the count of true positives divided by the number of actual positives. So if we were looking at this, figure, the blue are the true positives, and I would divide it by the total number of dots in this line. So both the purple and the blue. On the other hand, precision is going to be the count of true positives. So again, this number, the blue, divided by the number of total number of positive predictions. So everything that's to the right of this line. So the number of blue dots divided by the number of blue plus the number of green. And what you want with a model is you want a good balance of precision and recall. Because, for example, what's important to remember is that as I increase my threshold for certainty, let's say if I'm building my model, I say, listen, you predict that they will default only when you are 90% certain that they will default. So as I increase that threshold, I'm going to increase my precision. That is to say, the number of true positives divided by the number of true positives plus the number of false positives. But at the same time, my recall will go lower and lower. So there'll be a lot of people who default on their mortgages who I will not catch in my prediction. On the other hand, if I take my threshold for certainty and I lower it, my recall gets very good. That is to say, the number of true positives, people who default and I predict is defaulting, divided by the number of blue dots and then the number of purple dots, the people who default but I predicted would not default, right? But at the same time, my precision will go down. So there'll be a lot of people who I say will default who won't default. In other words, you have to balance these two. And so often what people do is they'll plot precision on one axis and then recall on the other axis, I should say. So let me ask you guys a question. Let's say I have, hold on. Okay. Let's say I have recall versus precision, and I have a precision recall curve that goes like this, and then I have a second precision recall curve that goes like this. Which model do you think is better? Is it going to be my blue model, or is it going to be my red model? So Nana says it's red, and why do you say that, Nana? Nana's absolutely right. They say that the curvature is low. So we could think of it in terms of the slope, right? The slope of this line is steeper than the slope of this line. Or we can also think about it in terms of area under the curve. So there's more area under the red curve than there is under the blue curve, which means that there's less of a trade-off between precision and recall. That is to say, it is possible to have a model that has high precision and high recall. So there's not this huge trade-off that we see here. So when we are evaluating the fitness of our metric, right, when we're evaluating the fitness of our model, there are a few things that we want to keep in mind. One, what is the baseline? For example, if 90% of people don't have a certain disease, and my model correctly identifies people who don't have the disease 90% of the time, that's not very good, right? That's not better than the baseline. And then the second question is, in addition to looking at accuracy, it's important to look at precision and recall. And whether you give more importance to precision or to recall will depend on what is important for your model. So for example, if we're dealing with our question of who's going to default on loans, if the bank I'm working for says it's really important that we catch the people who will default, and it doesn't matter that much if we incorrectly identify people who will default but actually don't default, well, then we're going to want to have very high recall on our model. However, if the bank says, what we really don't want to do is falsely predict that people are going to default. That is to say they're going to default when they're not defaulting. And we don't care if there are a few people who are actually going to default and we miss them. That's not important. So I might raise precision to the detriment of recall. So while it would be great to have this perfect flat model, well, it'd be great to have this perfect flat model that we see here. What we really want to do is make sure that the metrics we're using for our model are in line with the priorities of the stakeholders who are building that model. So Nana has a follow-up question. They say the problem is that all these metrics are available to you during the model building phase. Say you calibrated the model once and then pushed it into production. Okay. And now you're watching your model at work without recalibration. How do you know to pull the model off production due to low actual predictability power? Well, what you might do is you might set, I mean, I would imagine you have some sort of goal that the stakeholders have. And at some point, you're going to go, well, this model is not performing in line with what we want. So let's pull it off. I wouldn't say like as soon as you get below 80%, you have to pull it off. 80% in some contexts might be very good, right? So it really depends on, what you want the model to do and what you will tolerate in terms of performance. This is a little bit fair. Let's try that. That looks a little bit better. Okay, good. So I hope none of that answers your question. What were some other questions that we were dealing with earlier in the, let's see here. Okay, so Tululupe had a question about response encoding. So Tululupe, tell us a little bit more what you understand for response encoding. What is response encoding? Okay, so before I jump into Tolulupe's question, Pisan has come up with a different, let's see here, a related question to Nana's, which I think we can talk about quickly before we take a look at your question, Tolulupe. So Pisan says that they need false negatives as low as possible, but false positive signals annoy me should be kept low as well. I'm seeking which metric is proper in this case. Well, let's see here. If you want your false negatives as low as possible, the metric that you should be looking for is going to be recall. You want to get your recall. You want to favor recall over precision. Now, keep in mind that the lower you push your threshold for false negatives, the more you're going to get false positives. That's kind of the precision recall, problem, right? So keep that in mind. However, if what you truly want to do is reduce false negatives, you want to look and reduce recall. Okay, so reducing the number of categorical features to a limited number, that's Tolulupe's question when it comes to this. So let's take another look at the California housing data set. So I'm going to look in, excuse me, I'm going to look in linear regression. And for the linear regression, we have done some work with, no, it's not here. Where is it? No, I guess it is here. Hold on, where's my California data set? 1 second. Okay, well, let's see here. So we're talking about, so Tolulupe is interested in natural language processing in particular. So let's take a look at that. I'm going to just go all the way down. There we go. Here's our bag of words model. Okay, so there are a few ways to reduce the number of features when you're dealing with natural language processing. The first thing is, let's just remember that when we are doing natural language processing, Tolulupe is right. If we're doing the bag of words model, we end up with so many features to fit because we're looking at every word in the entire corpus. And then for each document in that corpus, we're seeing whether those words do or do not appear and how many times they appear. One way to reduce the number of features is instead of using a count vectorizer, which looks at every single word, you can use a hashing vectorizer. And a hashing vectorizer, what it does is it has a fixed number of values to which it will assign it has a fixed number of features that it will associate with the words in your corpus. Now the default is, let's see here, a million. A million, well, 2 to the 20th. And so if you wanted to reduce the number of features, if you go to hashing vectorizer, hashing vectorizer, sklearn, there is an n features argument where you can reduce the number. So you can say instead of 2 to the 20th, let's make it 2 to the 10th. Another thing you can do is that if you're using n-grams, you might have well, you can reduce the number of n-grams in the sense that you can have it as the default where there are no n-grams, or you can have only, say, from n-grams that are 1 or 2 long. So the dog, the cat. The other thing that you can do, not in this vectorizer, but if we go to a package called gensim, which I believe we discussed briefly last time. Let's see here. Oh no, it's going to be in the, let's see here. Gensim n-grams. Yeah. For the phraser, which is the thing in gensim that creates the n-grams, you can create a threshold for the n-grams. So for example, it won't take every single combination of two words, like if you have a sentence that's the cat is black, it won't be the cat is black. It will go over your entire corpus and it will only include an n-gram if it appears a certain number of times, right? So black cat might appear 10 times in the entire corpus, and then and only then will it be included. So that is a way to reduce the number of features in your corpus. And then another way to do it would be if we go to dimension reduction, you can do something like principal component analysis. Let me just run this really quick. Which will use a sort of a mathematical algorithm to, if there's sort of redundant data in your data set, it will reduce those number of features to the features that are most kind of relevant or different in and amongst themselves. Now, I won't go over this entire notebook, but that's how you might go about doing dimension reduction, both in an NLP context and then also in a non-NLP context. I hope that answers your question, Tolulope. Okay, what other questions can I answer for people? We have about 15 minutes left. Let's see here. For PCA, what does the covariance matrix represent in the NLP context? Is there any references I can read about it? Boy, that's a really good question and a very advanced question. So in principal component analysis, regardless of whether you're in the NLP context or not, okay, so there are two answers. The first is in the NLP so if we're doing like something like bag of words, right? In the NLP context, it would be the words that tend to co-occur with a given label. And for that reason, each of those words individually doesn't add, excuse me, all of the presence of each of those words basically gives your model the same information. So for example, if we're creating a spam detector that will separate spam from non-spam emails, there are a bunch of words that are always associated with spam. So for example, you might have, I'm trying to think, you might have like mm, lottery, winning, jackpot, uh, ticket, millions, all of those different words in your feature matrix essentially point to the same thing, which this is spam. And so what PCA might do is say, well, you don't need to worry too much about, uh, you know, millions and winnings. So we'll just reduce it all to say uh, a single feature that takes into account all of those words. And then in the other context would be like if we were doing a word to vec model. And keep in mind, let me just put myself up here. So keep in mind when we spoke about word to vec last week, we were talking about how words are embedded in a multi-dimensional vector space, right? And they might be close to each other, and some of them might be kind of on the same plane within that vector space. And so what PCA might do in that context is say, you know what, you don't need to worry so much about the X, Y, Z axis, but we can reduce this to only an X and Y axis, and you can still see the relationship between the different words. So you're basically removing an axis, an axis. All right. I hope that answers your question, Nana. Uh, Lupe, I see you're interested in non-negative matrix factorization. Tell me where in the notebooks are you looking at it particularly? In dimension reduction? Okay. So Victor has a question where they once saw that PCA is not as effective as TISNE To what extent is that true? You know, the truth is I don't have a good answer to that. But if you read that somewhere, I would love to hear more about it and more about what you feel like was the case there. So please let me know. Okay, so let's get to, let's roll down here to, where are we? Details, choosing the right commands, non-negative factor factorization. Okay, let me just download this here. Give me a second while I download the data set. I think the important thing to remember about non-negative matrix factorization is that when NLP, or excuse me, when PCA is looking to create these reduced, these sort of new dimensions that take into account similar dimensions, what can happen is sometimes you'll end up with negative values in your feature matrix. And those particular non-negative, excuse me, those negative values don't work don't work in the context of natural language processing because you can't say that there is negative presence of a word. It's either there or it's not. And so NMF is a way to do dimension reduction in the context of NLP because it allows you or it ensures that you only have positive or zero values in your work or in your, excuse me, in your model. So we can see like here when we did some topic modeling, you can see that software ends up as, there's one topic about computers, right? And there's another topic about, looks like religion or Christianity. There's another one about Lyme, excuse me, not Lyme stuff. I was going to say either medical stuff or medical school stuff. So the thing to keep in mind about non-negative matrix factorization is it's what you do when you want to do something that's like PCA-like in the context of building a building like an NLP pipeline. All right, and next Lamine has a question about AutoML. Lamine, where's this question? Let's see here. Lamine is talking about the AutoSKLearn package. Let's take a look at the AutoSKLearn package. I have to say, Lamine, this is the first time I'm hearing about AutoML. So basically what it does is you decide whether it's a classification problem or a regression problem, and then it chooses it for you? I am very curious about this. Hmm. So basically it does all of the parameter tuning and model selection for you? Huh. Well, I have to say that this is the first I am hearing of it, and so I don't have um, a big opinion. I suppose this is a way to get a model up and working quickly. The only thing I would be concerned about is that it is a little bit, people complain that sometimes machine learning is a black box, and so I don't know what the model's doing, or, I don't know what's happening under the hood. This seems like it's kind of doubly that because you don't even know what algorithm is actually being used. That being said, it looks very cool. So if you experiment with it, please let us know. I might read through this paper later today. Let's copy and paste this here into the chat in case anyone wants to read through it. The other thing I would wonder is what's the training time on this if it's going through all of these different models? Taking into account past, huh? I gotta say, I'm very interested in this. It looks pretty cool. Lamine wonders if they're getting rid of data scientists. Never, never, because we'll all need to decide whether this is actually working or not. Hmm. Someone needs to maintain all this code too. And then it does its own ensemble? Very cool. Well, it seems that it does better than the other auto sklearns. Huh. Well, I'm very interested. Thank you, Lamine, for bringing this up. This is pretty neat. You know what? If we have time during our next office hours, because we're kind of running out of time, I'm kind of like, maybe we should try this. Okay, well, we have about 2 minutes left. So before we sign off, are there any quick questions that I can answer for everyone? Okay. Well, if there are no questions, then I'm going to take my leave of you guys. It was good to see you all. I'm glad to see you had a good weekend, and I'm looking forward to another week of data science. So I'll see you all tomorrow, and until then, take much care.